Hello guys, welcome to session number 9 of our KCET 2023 one-shot revision series. Today's topic will be mechanical properties of solids, and as you can see in the bracket it's written 0.86, which means approximately one question has come every year, and there have been years where there have been no questions from this chapter at all. But yeah, this chapter is pretty small and it makes sense why they prefer to give less weightage to it. In general, class 11 chapters have less weightage and all that. So before I continue, I would like to mention that I'm using a mouse, so please do pardon me for the bad handwriting when I'm using annotation on top of the image. So yeah, now I'll be continuing. First of all, I'll be talking about, as you can see, its introduction. So what are elastic bodies? They basically, elastic bodies are bodies that regain shape after removing the deforming force. So you might take example of a rubber band. So if you like pull it up to some extent and then leave it, it regains its shape. The same way plastic bodies. So yeah, I'll be using a highlighter. They regain shape after removal of deforming force. So yeah, this should have been removal regains shape after removing. Yeah, this should have been removal. Please do spare me. It should have been removal of deformation force or whatever. So yeah, the example is steel. So over here, it do not. Yeah, they do not regain the shape after the removal of deforming force. As you can see, I've written removal here. So yeah, these are plastic bodies, and this would be elastic body. And the example would be clay, or you can even talk about other examples similarly. So I've drawn a diagram to help you visualize it. So let's say there is a rod which is like having one end fixed. In this case, when you apply an external force, as you can see, F external, the elastic bodies always have a restoring force acting in the direction opposite to the external force. So let's say we put external force, then there would be an increment in the length, and let's call it delta L, just this much, the increment in the length. So when you like remove the external force, it regains its shape, which has it regains its shape due to reforming force. Like there should be restoring force. You can call it restoring force. That's why FR, and it moves back to its equilibrium condition. It moves to its equilibrium condition and restoration force. So that would be the introduction to it. Now I'll be moving on to the next part, which would be stress and strain. So this would be something which typically is an important part of the chapter. Along with a couple other things, of course. So stress in general, the definition is restoration force by area. It is not just force by area, it is restoration force by area. And typically in elastic bodies, the restoring force would be equal to the external force applied. So yeah, that's why we just write it F by A, because both of them it would be noted as the same. And yeah, let's take this body and we are applying force, and this area, the part where we are applying force, the surface area, or basically the area of contact rather, is A. So for that, NS meaning normal. So here under stress, the first one would be normal stress. So that the formula is given I'll be putting it in the box, would be F by A, where F could be external force or restoring force. As I mentioned, it's equal to F I've written. Under this, you have to know that when the force is being applied in the outward direction, it's called as tensile. It will be called as tensile force. Whereas the force, if it's being applied in the direction towards the body, it will be compressive force, as the names suggest. And next one would be shear stress. So shear stress would be tangential force by area. So that's why I've written use components, which means that let's say this area was at an angle, so let's say some theta angle. In this case, you have to make sure that you consider F cos theta, because that's the tangential force. We should use F cos theta. So I've written use components just like to emphasize on the fact that you have to take tangential, meaning using the components. But I think it's self-explanatory if I've written Ft, which means tangential, and you have to use components. However, highlight it because typically people might get confused. And here, anyways, the external force that I'm applying is tangential. That's why equal to F. So what happens is, if the body is like this and you apply a force like this, the body apply it on a book, and then you can see this will happen. This will move like it will displace by an angle theta. So this formula I've written it over here. I'll just put it in a box once again. So that one would conclude shear stress, and next one would be hydraulic stress, or you can also call it as there are other names. So hydraulic stress is like, as you can see over here, the body, when the force is applied like externally, the body will get compressed and there will be a change in volume of the body. So for this, the formula, however, would be HS, meaning hydraulic stress, by the way, is equal to delta P, which means the change in pressure, or you can just write it as P excess, which means excess pressure. So delta P meaning P external, or it could be P excess, you can call it anything. So that would be the formula. And next one would be strain. As you can see, I'll be moving on to strain. So strain, the general definition over here would be change in dimension by original dimension. So under that, we have normal strain, which is similar to this one, as you can see over here. So where there would be like a rod, and yeah, I'll be zooming a picture, and make sure that you look at these pictures carefully, because I won't be using the pictures again in the modulus part of this chapter. So yeah, there would be this rod, and then you're applying a force. After the application of force, the rod will stretch by a length, and let's call it delta L. So as I've written here, change in dimension by original dimension. So change in dimension was delta L, and the original dimension was the length L itself. So that's why normal strain, it would be given by delta L by L. So yeah, that is going to be normal strain. We have shear strain coming up next, which would be similar, just like shear stress. But over here, what would happen is, you have to notice one thing: when the force is being applied here, it doesn't matter how it's being applied, because over here we are not talking about tangential force or whatever. The definition is different. So when you apply the force, as you can see, the body, it will get displaced, like how I mentioned. It will become like this dotted line, meaning it is the post state of the body, and this line, dark line, meaning pre state, which means before application of force and after application of force. So after application of force, it would be the dotted line, and that would be theta, and x meaning the distance by which it was displaced from its original position. As you can see, this much is x. You can look at the diagram in NCRT, it's much better. So yeah, that would be SS, meaning shear strain. Over here, tan theta is equal to x by h. But if this approximation will come into handy every time in your class 12, especially the derivations will be having this. So as you can see, theta will be very small. That's why if when theta is small, tan theta can be approximated to theta. So that's why the final formula would be just x by h, where h is basically the height of this block. I've written it over here. So yeah, next one would be hydraulic or volume strain. And for that we'll be using the same picture like diagram from above, but what you have to notice is delta V meaning the change in volume. So new volume, if it's V dash, the change in volume will be V minus V dash, and that would be given by HS, which means change in hydraulic strain. So that would be delta V by V, which means change in dimension by original dimension, just like how the definitions have it. So yeah, that would be like about strain. Next one would be Hooke's law. As you can see over here, it basically, there's a statement in NCRT, but what it means is stress is directly proportional to strain is what he says. So when you remove this proportionality, it will become, there will be a proportionality constant, like there will be stress is equal to some modulus times strain if you remove the proportionality. So that modulus you can write it as is equal to stress by strain, like once you remove the proportionality constant. So here we have different kinds of modulus. Before that I'll be explaining this diagram which is given in NCRT, but I have labeled and written a couple of things so that you wouldn't have to read the entire explanation given in NCRT. It would of course benefit if you read, but I have, however, as you can see, I've drawn lines and typed the stuff which is like summary of it. So till a point, stress will be directly proportional to strain, which means the body will be following Hooke's law. That is till point A. And then if you apply more force, it will reach to till a point B. From A to B, what will happen is it is not a linear graph, which means I'll write it over here. If I write H and if I put a tick mark, it means it will follow Hooke's law. However, for this section of the graph, Hooke's law is not followed. However, you have to notice that till like from 0 till B, right, the body is going to be elastic. Keep that in your mind. I'm just saying it, I won't be writing it here, but till point B the body is elastic. So at B there are 2 points. It is at the point B is called as you can see, yield point. It is called as yield point. It's even written over here. It's called as yield point B. And this, when you extrapolate it, the sigma y, as you can see, is called as yield strength. So yield strength, yield point, you have to remember these terms because you never know what kind of question they ask. And from B to C, as you can see, there will be more force being applied, and beyond like B, what will happen is if you remove the restoring force, the body won't go back to its original state. And if you keep on applying, it will be following this graph till point D, which is called as proportional limit, as you can see, which is also called as, over here if you see what is happening is from point C till E, okay, it is called as plastic. As I mentioned above, it means the body is no more elastic. From point C till whatever force is being applied, it's called as like plastic state, which means it is no longer an elastic body. And from what point it is from C. So there might be an MCQ asking this graph, and there might be like from C to D, is it elastic or not? You have to remember what I've said. It is plastic. It is not elastic. And what is the point E? It's called as fracture point. As you can see, I've written fracture point. And one thing you have to know, I'm not sure if it's given in NCRT, but if the gap between D and E, right, like I'm telling the gap between D and E, if the gap is really large, then it means the body is ductile in nature. And if the gap is very small, like let's say D and E was like this, it was very close by, D and point E was very close by, in that case, as you can see, it means it is a brittle body. So yeah, this is like going to be something that you have to know from the graph. I hope it was clear. If not, you can always join my Telegram. The link is in the comment section, description, and you can ask me questions. I'll be clearing them for free of cost. Next one will be modulus. Like how I mentioned above, when you remove the proportionality constant, you'll be getting stress is equal to some modulus by modulus into strain. And when you send the strain, like when you basically divide it by strain, it'll be M is equal to stress by strain. So the general definition of modulus is basically stress by strain. Remember, stress by strain. I cannot write much like how I mentioned I'm using a mouse, but it'll be stress by strain. That would be the actual that would be the general definition. However, under modulus, the first type of modulus would be Young's modulus, as you can see, and denoted by Y. The formula would be stress by strain, but over here stress would be replaced by normal stress and strain would be replaced by normal strain. I hope you're getting it. It would be NS by NS. That's why I used like short form, so it'll be easier for you to remember, which means normal stress by normal strain. And the formula obviously is given above, so when you replace it, you'll be getting this formula. Next one would be shear modulus, which is denoted by the symbol G. So shear modulus is again given by stress by strain, but over here it would be SS by SS, which means shear stress by shear strain. And replacing the formula given above, it would be this. You can look at the diagram. I've saved like space in order to include all of this over here. Next one would be bulk modulus, which is given by beta, and for that again it would be, as you've seen above, volume stress by volume strain, or basically I think it's mentioned by hydraulic stress by hydraulic strain. And the formula is given above. But one thing, if you notice, its minus sign is included. The reason why it's minus is because there is decrement in the volume. The change in volume, when it happens, like if you see the volume is getting decreased, so that's why I've included a negative sign. It only means that the volume is getting decreased, so that's why there's a minus sign. And you can also instead of like let's say delta, you can also include D. That's why I've put dP by dV, or I've written and I've put it. Another thing is compressibility, which is a part of bulk modulus. Basically, it's just a simple formula. Compressibility is the reciprocal of bulk modulus. So that's just a simple definition of it. Next one will be similarity of this with the spring, basically. So as you know, this Young's modulus formula, when you like write it, it will become F L by A delta L. And when you rearrange it, you'll be getting it as F is equal to, like when you rearrange this formula, you'll be getting F is equal to A Young's modulus by length into delta L. This can be compared with this formula. As you can see, it can be compared with F is equal to Kx, which I mentioned in my, I think I mentioned it in rigid body dynamics, that this would be spring force, F is equal to Kx, where K would be the spring constant. I hope you watched the lecture. So that's why what you can see over here is K is equal to Ay by L. That's what you have to infer from this part of the chapter. So this part of the chapter, yeah. So next one will be potential energy. So potential energy, there are a couple of formula. One is potential energy is equal to half into stress into strain. So this is like a main formula, but what they can do is they can ask what is energy density. So if they ask you what energy density is, then you have to divide the entire thing by V. So that will become U by V. It is given by sigma, by the way. And I'll just write it over here. Energy density ED, I'll write it over here. ED is basically given by mu, which is equal to potential energy per unit volume, which is stress into strain by 2. As you can see, if you rearrange this, you'll be getting this. You can also use the formula U is equal to kx square, which if you remember I had mentioned in my same rigid body dynamics chapter. I think so, I'm not sure, or maybe it was the other chapter, work energy power. Yeah, work energy power. So here from the above analogy where k is equal to a Young's modulus by L, if you replace it, you'll be getting the potential energy formula, which is half kx square, but you have to replace k with this. So I'll be just highlighting it, it's important. You can expect them to just not give the typical stress strain formula. And we're almost done with the chapter. It's a pretty small chapter. I have, however, explained a lot. That's why it's like maybe pretty long, but it should actually be done under 10 minutes, or actually under 5 minutes if a person has revised it. But however, I'm explaining. So Poisson's ratio, it's given by the symbol sigma. So this what Poisson's ratio is, I've just like used another diagram if you do not understand mine. So if there's like a body like this, and then if force is being applied, if you can like visualize it, if you apply a force to a rubber band, the length will increase and its thickness will decrease. Or here D is thickness, by the way. It's not like diameter or anything. It could be diameter, but over here what I mean is thickness. D is thickness. I could have used T, but I went with the term D. I think in NCERT is given as D. That's why. So once you like apply some force, right, the thickness will decrease. It will become D minus delta D. This is dimension of the new body, by the way, after force is applied. However, the length will increase, which is L plus delta L. So it has increased by delta L, the length, and the thickness has decreased by delta D. So when you write the final formula, it will be minus delta D by D divided by delta L by L. The reason why minus is there is just like because of the fact that thickness is decreasing, like how volume decreased above in bulk modulus and minus was there, the same way. You have to include the negative sign. So with that, Poisson's ratio is done. Next one is elongation due to self weight. I'm not sure if you find it, if you're able to find this in NCERT, but there is a derivation for this, and I think if you remember the final formula, which is easy to remember, it will be more than enough. So yeah, over here I've given the same analogy so that you won't forget, because this is an analogy which you have to make with the spring. It's like different chapters, and a good analogy can be made. So yeah, I'll just highlight it. And the final formula is the elongation x. The elongation is given by x. Like basically, let's say that you have a rod, and then you hang it like this. The elongation after some time, because of its own weight, it elongate by small distance x, right? Like visualize it. Imagine you're like hanging a heavy rod. Due to its own weight, it will elongate by small distance, and that distance is x. It can be given by mg by 2 divided by mg by 2 into L divided by ay, where y, capital Y is Young's modulus, and m is mass, L is length, and a is basically area. And we know what g is, small g. It is going to be the acceleration due to gravity. So with this, I've completed the chapter. Hope you guys liked it. You can like the video, share it, and subscribe, and that will benefit the whole benefit the community as a whole. You can also ask me doubts. All the best, work hard, and see you.